Excellent. Thanks a lot to the organizers for putting this together, and also to all of you for being here. So my task is basically to fill you in on startups that we have in Germany, which we think are very promising, namely our own, on neutral atoms. And also what I want to do is pitch a little bit the idea that, of course, in Europe we have very promising initiatives, both on the fundamental research side, and also we want to, of course, translate that to an industrial setting. So this is what I'm up to, but I want to start at the basics, just reminding you where we are coming from, and sort of, reminding you all of what this year is. It's the International Year of Quantum, and of course, we remind ourselves and remember sort of the great founding fathers sort of quantum theory, who are all sort of, laying the groundwork of what we are relying on today. And of course, quantum mechanics has influenced us a lot and influences us every day today, in that we rely on semiconductors, of course, we rely on medical imaging driven by quantum technologies, and of course also our GPS heavily relies on quantum theory. So this is all sort of quantum technology that emerged from the first quantum revolution, basically brought to us by these first founding fathers. But now we are looking at the sort of tipping point, inflection point towards the second quantum revolution, where now we are building complex systems. In particular, we can build quantum computers. Why do we need quantum computers? Of course, this is probably nothing new to you. Well, the idea is that in a problem space, where all problems lie, we have easy problems, like summing 5 and 2 or multiplying 5 and 17. Every one of you can give me the answer. A classical computer can also do that. But there are also problems like, for example, calculating the structure or dynamics, reaction dynamics of a molecule that are hard for a classical computer. And nevertheless, those are, of course, extremely relevant problems, because they may give rise to personalized medicine, for example. And the point is now, if we have access to quantum resources, we can use quantum computers that have an exponential advantage over classical computers to actually tell us what the reaction mechanisms or the structure of these molecules are. And this idea that quantum resources are important, of course, is something that was brought to us 3 decades ago, roughly, by Richard Feynman, who told us that if you want to simulate quantum mechanical systems, don't try to use a classical computer, use a quantum computer. Use quantum resources and make your simulation of nature quantum mechanical to learn something about a quantum mechanical nature, because the classical computer is doomed. So why am I telling you this? Well, Feynman actually told us that the first thing you should think of is how to simulate quantum systems. And so the first part that I will focus on here, and this is a bit of the history, or the scientific history of also what Planck builds on now, is how to actually build a quantum simulator. So what is a quantum simulator? Well, a quantum simulator is an analog device which can solve a very specific problem. And the idea that such analog devices exist was basically invented in Europe, was invented by Ignacio Cirac, who's now in Munich, and Peter Zoller. At the time, both were in Innsbruck, and Peter still is. And the idea is that we can do material simulations using cold atoms trapped in periodic structures, crystals of light, so-called optical lattices. So what is the idea? Which problems can we actually address with these simulators? Well, the idea is that if we look at the material, at the heart, materials are, if you simplify, of course, a periodic arrangement of positively charged ions and a couple of electrons that rattle around these ionic cores. If you look at the typical parameters of such a material, the density that you get in such materials are about 10 to the 24 to 10 to the 25 per cubic particles per cubic centimeter, and the temperatures at which we study these materials are in the millikelvin to Kelvin range, so at room temperature, or we can put them in a cryo to cool them down. Now, what does a quantum simulator do? Well, we want to learn something about a quantum material that we otherwise cannot study by translating this problem to a very different parameter regime, however, in a way that the characteristic scales are the same. That the quantumness, if you want, characterized by the de Broglie wavelength divided over the typical distance, is exactly the same in both of these cases. And we can do that actually by going to low densities, trap the atoms in an optical lattice, and cooling them to nanokelvins. And so you can learn something from this system about the other system, just doing experiments in a completely different way. And this is actually not just a crazy dream. This is something that is reality in the labs. Actually, it's been sort of shown for the first time that this concept works in 2002 by Emanuel Bloch, now scientific director at Max Planck Institute of Quantum Optics and a professor at LMU Munich, who actually showed that you can study material properties this way. And not only that, in subsequent studies, he could also show that you can use microscopes to actually microscopically look at these atoms, control them, and learn stuff that you cannot learn from a sort of block of material because you don't have microscopic access. So looking now at this idea of quantum resources, what is the benefit of using such simulators? The benefit is actually that if you compare the performance of a simulator, here is a graph from a paper of a few years ago, and you look at how precise you can simulate quantum many-body systems, so the systems we are thinking about here, with classical means. So this is quantified by a simulation error. You see that a classical computer actually does very poorly. The error in the simulation blows up very fast. However, on such an analog quantum simulator, you can actually keep the error under control, and you can make meaningful predictions in a range where you cannot even hope to do classical simulations. So you already, in a sense, have an exponential advantage here, and it can even be a larger advantage on very specific problems, but you still have it, and this is, of course, a very promising way forward. Nevertheless, it's not everything, right? In the end, what we want to get to is we want to get to problems that are useful, also industry relevant, and it might be that there's some industry relevant problems in this space, but this is something that is active research. If we want to address sort of more general problems, of course, what we need to do is we need to go digital. We need to build a universal quantum computer. And the idea is that a lot of the technology that was developed on the scientific frontier in order to actually make these quantum simulators can now be translated to build universal quantum computers. And this is what I will tell you today. Again, actually, the initial ideas that I'm going to present now date back to ideas of Ignatius Dirac and Peter Zoller, so you can see their influence, actually. And the idea is that you can actually use neutral atoms also to build universal quantum computers. What is the main idea? Well, the main idea is that we build registers of atoms where we trap the atoms in thousands of optical tweezers, tightly focused laser beams, and hold them in ultra-high vacua. So here you see a spot array of these laser beams, and we can really scale this to tens of thousands, even 100,000 are possible. And the way you can think about this is that our register is basically formed of individual atoms that are stored in a crystal of light, and we control the qubits using these focused laser beams. Why is that relevant? What are the selling points here? Well, first of all, as I already showed you, these systems are amenable to the analog simulation mode. So we can actually already do some material simulations on these systems. However, they can, of course, also be brought to the digital realm. The energy consumption of these systems is extremely low because you only have to supply the laser power once, and then the systems scale. Yeah? So this is not like superconductors or other modalities that have sort of a growing power requirement, so the required power overhead is very modest here. The reason connected with that is that our systems operate at room temperature. We don't have to go cryogenic, and we can also develop them to a stage where we can put them in a data center. So everything we have on the laser side can be put in racks, and the physics packages also, as I will show you. Another point, coming more towards this bigger picture of where does Germany sit, what is Europe, what's the international situation? Well, if you look at the technologies that go in here, lasers, vacuum, and so on, they're actually basically very prominent in Germany. Photonics, very big, and one could actually say that Germany and the European Union are actually world leaders in these technologies. So sovereignty is a strong point. All right, so this is our register, this is the platform. How do we store qubits? Well, the idea is that each point that you see can hold an atom, and every atom can actually store quantum information. So we can store qubits in each and every atom. And the way this works is actually we use the internal states of the atoms, the electronic states, the spin degrees of freedom to encode quantum information. This is extremely coherent, so atoms are also the basis of the world's most coherent clocks. So the coherence times we can reach are unparalleled compared to other modalities. Now, how do we do gates? Well, in order to make gates, what we need to do is we need to actually make sure the atoms can interact. So we need to be able to sort of connect two atoms in a specific way. And in order to do that, what we do is we actually, again, take lasers, we excite the atoms to highly excited states, Rydberg states. You can essentially choose your principal quantum number that describes this Rydberg state. And at that Rydberg state, the atoms would very strongly interact. To give you a sense of scale, if you think about sort of the core of the atom, the core of the electrons around the nucleus, and you sort of give this the size of a baseball, then this Rydberg atom that we generate would actually be larger than the size of the baseball stadium. So these are extreme scales at the scale of a single atom. And this gives rise to this very strong interaction between atoms that allows us to do quantum gates. So how well do these quantum gates work? Well, this is a demonstration that we did very recently in our labs at the Max Planck Institute of Quantum Optics and at LMU Munich. And gate fidelities that we can reach here are at the moment about 99.5%. This is nowhere near the physical limit. And the nice thing about this is that this is in a sense, scalable entangling gate. So it doesn't matter whether we do this on 4 pairs, 10 pairs, 100 pairs. In this case, we actually did it on 8 pairs in parallel. This will just scale. And this is an extreme advantage compared to other modalities where you have to calibrate, have a large calibration overhead. All right. So this is, of course, also what drove us forward to say, OK, building on these groundbreaking physics and scientific ideas, let's actually go one step further. Let's basically bring this to industry in a non-academic setting. So in 2022, Alexander Glätzle, Sebastian Blatt, and myself founded Planck with exactly this vision that we take the scientific research and we bring it to market. By now, we've grown to about 80 people. This is growing every day, and we've received quite some orders and investments that I will talk about in the following. Still, we keep close to our roots, so we are deeply sort of intertwined in the Munich Quantum Valley. The Munich Quantum Valley is a local initiative in Munich, actually also including groups in all of Bavaria that was generously funded by the Bavarian state and by the by Germany. And this is a huge talent pool of about 70 principal investigators working on quantum computing and quantum technologies, and more than 270 scientists on this topic. And we are proud to be one of the first startups, actually the first startup focusing on quantum computing, emerging from the Munich Quantum Valley and sort of in that sense standing on the shoulders of giants and on the shoulders of a lot of excellent scientific work. This is also important to stress. So the Munich Quantum Valley was actually founded and was initiated with a clear goal to establish startups. So it is an academic initiative, but the fact that there has to be some push to market, some commercialization effort, not just fundamental science, was highlighted already by Chancellor Merkel when she visited our institute in 2021. And it also ended up actually in this Handlungskonzept Quantentechnologien of the federal administration at the time. And so we are proud that we can actually contribute our part to this mission to basically build this German quantum computer. What is the sort of business model of Planck? So where can we actually sell products? We have essentially 3 streams. So we have a cloud stream. So we are preparing a machine that will be put on the cloud so industrial users can use it, can run calculations on it. We also are building on-prem machines. Examples will follow, where if users are interested in running or putting a quantum computer on-prem and running simulations or computations on it, we would supply that. And we also have a strong theory department focusing on algorithm development that allows us to explore together with customers whether there's a quantum advantage in certain areas. So what use cases do we look at? Here's our portfolio of use cases. So these are all projects sort of with different partners. And you can roughly get a flavor of the breadth of these projects. So we look at a variety of different things: quantum machine learning, battery simulations, so material simulations, logistics. And also, we have a big push on computational fluid dynamics, where the idea is to use quantum-inspired methods based on tensor networks to enable calculations in this new description, which you cannot do with conventional methods. One has to say, actually, that all of these use cases are, or all of these projects are open-ended, so we partner with these partners to see if there is actually an industrial use case in the sense that there's an economic worth there. So for none of those, it's at the moment clear, but this is part of the project that we're working on. On the hardware side, we also have two big projects that I want to briefly highlight. So we have one project where we sold a quantum computer to the German Aerospace Center within the Quantum Computing Initiative. It's the DNAP project with the goal to build a quantum computer with 100 qubits that we will then connect to 2 logical qubits, just to prove that we can do that. And the project is still running for about a year and a half. The second project we have is one that sort of foresees that quantum computers will be useful in a high-performance computing environment. So we have a joint project together with LRC, the Leibniz Supercomputing Center, where we will put a 1,000-qubit machine in the LRC, included in the HPC workflow, and basically see how one can actually improve the performance of HPC using quantum. So how does such a computer actually look? So our quantum computer, eventually, this is a prototype, well, it's not just a model, this will actually go in racks. And so the core of what we are developing is this physics package you see here in the center. So let me take you sort of on a ride into this physics package. So this is a short video that comes from the Max Planck Institute of Quantum Optics. And you can see how we are now flying into the physics package. You see this is where the objective sits. Then we have a glass cell, and inside the glass cell here you see a flashing cloud of atoms. These are about 1 million to 10 million atoms, so we have a huge resource overhead in terms of qubits, and our challenge is now to basically implement the local control to make these useful machines and to add the gates, as I've shown you before. What is the path on which we are? So we basically take it step by step. As I already showed you, we have a vast track record on analog quantum computers. We are now starting to build our first digital machines with the gates that I showed you on the science side. And of course, we are going to translate that to the company. And then, of course, we are also working towards fault-tolerant systems in the long term that can then actually unlock the economic potential of quantum computers. All right. Now, in the last few minutes, I actually want to zoom out a little bit and basically make us all think a little bit what is actually required to build the world's best quantum computer. So we already heard a very negative perspective. I'll try to phrase it slightly more positive. So what do we need? Well, what we need is we need talent. We need highly skilled, highly specialized quantum scientists and engineers that can actually do the job. It's not enough to just talk. We need the people on the job. We need the people to be able to do quantum physics and to build these machines. We also need strong academic partnerships. As we heard, there are actually potentially still some unsolved academic questions, or actually there's optimization potential on the academic side by being sort of, a bit more broad in the exploration space rather than just focusing on the engineering. So we need to establish strong relationships with research institutions. We need public funding, so quantum computing is a publicly supported market, and this will probably be like this for some time until we have early adopters from industry that put significant amount of money into the field. We need access to a robust supply chain. Yeah? We cannot rely on deliveries from outside Europe, I would say, also because of dual-use regulations that become more and more pressing. We need industry customers and early adopters to actually buy these machines, to get engaged, and also use them to also basically establish relationships and showcase, of course, the advantage of quantum computers. And last but not least, we need venture capital to actually allow startups to grow and not stop at a very exciting stage when they're ready to grow, because there's no venture capital in Europe in general. All right, so where do we stand on all of this? Well, if we look at scientific publication, Europe is top. Yeah? So we have, among the nations that we compare here, the largest output on scientific publication in quantum technology. The same is actually true if we look at talent. So the number of graduates in Europe is very large, and talent is one of the big bottlenecks in this field. So we are in an excellent position. However, if we look at total investments from the private side, situation is slightly different. So here, the US, of course, dominates strongly, and this is a problem, especially when startups want to grow and become scale-ups and grow significantly. Nevertheless, if we look at this study from the World Economic Forum that was published earlier in the year, they actually foresee that Europe has a unique opportunity, combining the knowledge, combining the scientific expertise in actually making quantum technologies a beacon of hope of an opportunity for Europe. So I think this is the positive note that I want to end on. Actually, almost, I want to show you our continuously operated array of 1,200 atoms that you can see here, again, work done at the Max Planck Institute of Quantum Optics that really, in my mind, or my view, shows the extremely good scaling potential of this platform, and we're excited for the way forward. And with that, I'm at the end. We have 5 seconds also. I'm happy to take a question, of course.